Welcome to our NPTEL lectures on advanced power electronics and control. Today we are going to discuss three-phase converter. We have discussed in details with the single-phase converter. Now we are discussing with the three-phase converter. We start in the same fashion as we have started the single-phase converter. Since actually our supply is three-phase, three-wire or four-wire system, and it makes sense for the high power applications, for the DC motor, mostly this kind of applications, we convert directly three phase to DC. So, this is the application part of it. So, we use, this is basically three phase half wave uncontrolled rectifier fed through the diodes, and it is feeding, let us assume that RL load. So, what happened? You can see that how conduction takes place. So, diode D1 will actually, when it will conduct, basically that will the voltage drop across it will be 0, and then you will get a voltage of VAN across this dot RL. If D2 is conducting, then at that time basically it will block the voltage when D2 is conducting. D1 will block the voltage of VBA, it will be a negative voltage, and similarly it will block the voltage of the VCA. So, similarly when diode 2 was conducting, so the third diode will block VAC, sometime BBC, and once actually diode 3 is conducting, then load will get the voltage VCN. So, load will get the voltage depending on the 180 degree mode of conduction. For 360 degree VAN, BBN, VCN, most positive phase will conduct. So, accordingly you will get the three different voltages. So, let us see how it works. This is actually the three phase voltages, and our starting point will be actually this point, where the voltage A actually cross over the voltage C, and thus voltage A become the actually most positive step. You can see that till this region, that means actually pi by 6 to 150 degree, actually most positive phase is the VAN. So, definitely this will conduct for actually pi by 6 to 150 degree. So, this will conduct. Similarly, after that, you know, VB actually at this point crossover takes place. So, since there is only single diode in upper limb, so crossover takes place, and it will have a crossover at this point where B phase becomes most positive phase, and thus it will conduct till this point. Similarly, VC will conduct after actually the period 270 degree, and so on. So, till this time D1 conduct, till this time D2 conduct, till this time D3 conducts, and thereafter till this time D3 conducts, and this is the output voltage. We will have a third harmonic oscillations, we can find it out by analysis, and this is actually the voltage blocking state of the different diode, and this is a VD1. VD1 will conduct actually this point to this point, so it will be blocking the voltage red 1. Similarly, VD2 will have a this kind of fashion. So, and same way VD3. So, it will conduct when actually at this instant. So, you will get a negative. So, phase A or red phase will conduct for pi by 6 to 150 degree, for another 20 phase B, and another 20 degree phase C. So, thus due to the RL load, the converter operates in a continuous conduction mode if you assume that load current is quite high, as diode blocks the negative voltage, the diode only conducts in that phase where the phase voltage is maximum of these 3. As shown in the waveform, the phase current has DC component which flows through the AC source and makes a DC saturation in the AC side of the transformer. For this reason, this kind of configuration we do not prefer. So, it may leads to the saturations of the input transformer. So, 3 phase half wave uncontrolled rectifier, let us see that what are the different values what we have seen in the actually single phase. So, we have actually VAN, VEBN, VCN, these are basically phase voltages, and so output voltages you can see that from pi by 6 to 5 pi by 6, that means actually 30 degree to 150 degree, it will get a voltage of VAN. So, you write the VAN and you calculate over it. Similarly, you can calculate actually output RMS voltage, that is basically you get 3 such cycles. So, it is multiplied by 3. Same way for RMS values actually multiply by 3 pi by 6 to 5 pi by 6 root 2 Vm sin omega t square dt. So, you can get this actually the values for this RMS values as well as the average value. You can calculate, I left it to the student to calculate. So, similarly you can have the load current, so that is V average by R. Similarly, IRMS equal to, it should be same input RMS, that will be same for, since it is a balanced system, IA, IB, IC should be same, and we can find it out that its value will be actually I0 by root 3. So, input power factor, that is active power output, which we have shown also in a single phase system by RMS input. So, that is basically IPF, that is a voltage average into current average by 3 into VI into RMS. So, from there we can calculate basically the IPF. Now, since we have discussed that this mode of this actually configuration is not preferred, because it leads to the saturation of the transformer and the rate of the conversion of the power is very low, generally use full control devices. The 3 phase full wave uncontrolled actually rectifier with, let us consider the RLE load. Now, in this condition, one diode from the upper leg and the another diode from the lower leg will conduct, and we will actually, since one diode will conduct for the period of 120 degree. So, we have a different way to actually nomenclature it. Since D1 will conduct after 180 degree of its conduction. So, for this reason actually nomenclature will be have a difference of 3. So, that is D1 and D2, D1 and that is D1 and D4 will be the first leg, and similarly D3 and D6 will be the second leg, and D2 and D5 will be the 6 legs. The combination is the odd combination will be up. So, D1, D3, D5 and D4, D6, D2. If you do like that, then you will find that actually this sequence will come. If you name it this way, actually this sequence will come. So, for first 60 degree, so of course we start from the point where actually phase A and C get intersects at this point, and we have split it from this point for 60 degree intervals. So, it starts from pi by 6 to pi by 2. So, what happened in that configurations, that D1 and D2 conducts, and when diode D1 and D2 conducts, for this is you can see that these are 0. So, and it is the ones actually thereafter what happened, diode D2 D3 conducts, thereafter D3 D4 conducts, and D4 D5 conducts, D5 D6 conducts, then D6 D1 conducts, then after D1 D2 conducts. So, this will be the actually the column you will get as zeros. So, here D1 D2 conducts, thereafter when D3 D4 start conducting, it is blocking the voltage of VBA and VCA. There it is blocking the voltage of actually VC and VCB and so on. So, these are the pair of voltages it will continue to block, and accordingly you can actually find it out which voltage it is blocking, and you can get the output voltage accordingly. So, for this reason, in load voltage will be delivered for the first 120 degree by actually D1 and D2, first 60 degree by D1 and D2, and thus you get a voltage of actually VSE. Similarly, when D2 D3 conducts, you will get a voltage of BC. Thereafter, when D3 D4 conducts, you get BA. When actually D4 D5 conducts, you get CA. When D5 D6 conducts, again you will get actually reverse CB. Then when D6 D1 conduct, you get AB and so on. So, these cycles will continue, and one pair of actually diode will conduct for the 60 degree, and thus and one single diode will conduct for the period of 120 degree. So, this is actually waveform. So, we can see that the RLE load represents the DC motor or the battery, and the load side inductance is quite high to keep the load current continuous. So, we have a ripple, but actually this is the IDC value, and the load current is assumed to be continuous. One diode from the upper side, that is D1, D3, D5, and another diode from the lower side will conduct at a time, but no two diodes from the same lake will conduct simultaneously, otherwise actually lake shorting will take place, ultimately no voltage will be delivered at that time to the load. So, it has 6 different diode mode of conduction, these are D1, D2, D3, D4 and so on. Each diode will conduct for the, as I told you, 120 degree, a pair of diode will conduct for the 60 degree. So, this is the waveform it. So, D1 will conduct, actually thereafter D3 will come into the picture, thereafter D5, thereafter D1 again. Similarly, at this time D1 and D2 will conduct, thereafter after actually at this point D2 will be actually the D1 will be the outgoing thyristors at 60 degree, and D2 will conducting, and D3 will be the incomings. So, similarly it will conduct like that, and since there is a 6 such changes in 360 degree, so you will have a 6 pulse waveform, and this value is given by under root of 2 VL, and we assume that load current to be constant, and this will be the pattern of the input current. Input current will be the stepped square wave. So, since actually this time D1 conducts, so for this reason what happened, current will be positive. Thereafter, after interval, you can see that D4 once start conducting at this region. So, we will get a negative pulse from phase A. There are again another pause of 60 degree, again it will pick up. So, in a cycle of 360 degree, it will conduct within positive and negative cycle. For mode of 120 degree, there will be a pause of in between 60 degree. So, there is a sufficient time to actually commute. Similarly, this is a current for phase B and phase C, and this is the waveform drawn. This is the fundamental of the input line currents. Now, few parameters comes into the pictures. Now, for as we start from this actually pi by 3 to 2 pi by 3, and VAC is the amount of the voltage comes into the picture. So, output voltage will be given by 3 pi by 3 to 2 pi by 3 VL sin omega t. From there we can get this basically the value of the RMS voltage. RMS voltage you can find it out, at is 1 plus 3 root 3 by 2 pi into VL. So, from there of course, you got an RMS voltage, just divide by the you can find it out the current. So, current will be basically root 2 by 3 into, which is assumed to be constant, that is output load current, and that our output load current is given by this basically VOAV. So, that is the average voltage, that is root 3 by 2 by pi into VL minus E by R. So, from there we can calculate the RMS voltage as well as the RMS current. So, input power factor for IPF will be the active power output by RMS power input. So, now let us see that what happen if this actually 3 phase full wave uncontrolled rectifier fitting an RC load. That is quite common, actually most of the application nowadays are the adjustable speed drive. In case of the adjustable speed drive, actually you can have a variable kind of load, and what happen, we feed to an inverter to run it in the drives in a different manner, and for this kind of waveform is quite common in case of this actually in different kind of industrial applications, and this capacitor essentially actually filter out the ripple and gives you more or less a constant DC voltage. So, similarly this is a 3 phase waveform as we have discussed. So, here what will happen till the input voltage, this input voltage VAN is more than VAC, that will not conduct. So, output voltage it will hold by the capacitor, this will have this kind of value. We will have ripple that depends on the load current as well as the size of the capacitor. So, due to that what will happen if so till this voltage is more than this voltage, that will not be forward bias and thus no current will flow, and thus that current might be peaky. So, it will conduct for the D1 D2 will conduct for this very small interval of time. Let us see that it is alpha plus alpha to beta. Similarly, current will have this kind of choppy profile, and it is quite disturbance, and it is a unique problem to be solved for the, this is one of the issues with the power quality, because you can see that actually it gives a choppy current and you have actually a sinusoidal voltage. So, this is the problem once you have actually RC kind of load, and nowadays its prevalence. Now, let us come to the 3 phase half wave control rectifier. So, since most of the application we require a controlled source in DC kind of application, for this reason we prefer to have a control rectifier. So, there is a thyristor IT1 and there is no difference in between the diode and the thyristor. We require to trigger the forward most forward thyristors depending on the voltages, and automatically other thyristor will be naturally commutated, because if let us say that previously B phase was most positive and thyristor T2 was actually conducting, the moment actually A phase become more positive, so definitely the reverse bias will be applied and the thyristor will commute. So, for this reason what we require to do, let us assume that us start from the point where actually AN is a most positive phase and it has been given at an angle delay angle alpha. So, it will trigger at an angle alpha. So, that is the point where actually T1 will be triggered on. It will continue till conduction. Thereafter, when actually you see that actually most positive phase is actually T2 phase B, then T2 required to be conducted. So, each thyristors will conduct for a period of the same way 120 degree, and so this will be the profile of the load voltages, and like the controlled rectifier you get, since it is a, we assume that actually this load is RL type of load, and for this is the negative portion of the load voltage will come into the picture, and we assume, and since this is a load current is assumed to be constant, so we will have a input current will be given by like this. And but problem of this half wave rectifier or the converter is same, because you can see that actually this load current is positive in input side, and that leads to the saturation of the transformer. So, for this reason it is not at all used in most of the, we are phasing out it. Same way we have a calculations, we can do the calculations, that is we have a 3 pulses for 360-degree cycles. So, it is alpha plus pi by 6 to alpha plus 5 pi by 6. From there we can calculate the Vrms and Irms, and ultimately from there we can divide it by R to calculate the average current, and Irms you will find that I0 by root 3 by simple calculations, since it is a square wave. So, similarly we can calculate the input power factor, that is V output average into I output average into 3 into Vi into Irms. So, let us come to the more practicable solutions of the 3 phase, and where load is assumed to be highly inductive, 3 phase full wave rectifier, and same the nomenclature as we have used in case of the diode, that is T1, T3, T5. So, since it will be conducting and one pair of thyristors will be conducting for the period of 60 degree pi by 3, and one thyristor itself will conducting for the period of 120 degree. And what will happen here in this case, essentially we will have a same kind of actually nomenclature, that is T1, T3, T5 are the upper thyristors and T4, T6, T2 are the lower thyristors. So, you trigger the point where phase A and phase C is crossing over. So, you give an delay angle alpha. So, you will start from this point. So, T5 will be the outgoing thyristors from the top, and so T6 and T1 is conducting. So, you will get phase A, B across the load. Similarly, thereafter T1, T2 is conducting and you get a phase AC to the load. Thereafter you get T2, T3 is conducting, you get CB to the load, so on, and frequently you get. So, you can see that here it is conducting, so you get VAN to the load. Similarly, you triggered this lower thyristor here, thereafter you get VBN to the load, thereafter you get VCN to the load. So, here if you start from here, so first you get VAB, thereafter you get VAC across the load, thereafter you get VBC, thereafter VBA, thereafter VCA, thereafter CB, and this will continue. So, this is the configuration of the full control bridge rectifier. So, here it is same as we have discussed in case of the diodes. So, it is triggered for an angle alpha to pi by 6 before T1 is turned on, T1 and T6 is conducting, T6 is already conducting and T5 was the outgoing thyristors. So, the period alpha actually it is alpha plus pi by 6 to alpha plus pi by 2, where the point T1 T6 is conducting. And this is the actually the configurations. So, you get CB, thereafter AB and consequent voltages. At alpha plus pi by 2, T6 get actually turn on due to the reverse bias conduction and T2 get triggered. From this period actually alpha plus pi by 2 to alpha plus 2 pi by 3, T1 T2 both are conducts. So, thyristors are according to be triggered in the sequence T1 T2, T3 T4, T5 T6 and so on, and this is basically assuming that there is a constant load current. So, this is the current through the thyristor T1 and this is the current through the thyristors T4, that is the lower leg of the phase A, and thus load current. So, the source current will be this and load current will be this. Since it is a positive and negative cycle, so it can be used in case of the transformer also. So, it does not lead to the saturation of the transformer. Similarly, we require to calculate that actually Vrms and the average voltages. So, students are requested to calculate these values, actually this is simple integrations and it is available in normal any textbook. So, this is the pattern, same way we have discussed in case of the diode. Now, this is the this is for actually half control rectifier or converter. So, here upper legs will be thyristors and lower legs will be diode. So, you have a control over triggering the thyristor and automatically actually negative phase will be triggered depending on the actually which phase is most negative. So, thus what you can see that, let us see that again nomenclature will be the same as is used in case of the full control converter. So, it is D4, D6, D2. So, when T1 and D1 is conducting, so voltage across the thyristors 1 is 0 and it will continue till 60 degree, thereafter it will be blocking the voltage VAB and ultimately the what will happen. So, these are the voltage they will be blocking throughout it. And so, similarly when D2 is basically conducting T1, so and it will be conducting for the period of 120 degree. So, it will conduct till 30 degree to 150 degree, thereafter other voltage will follow like that. So, again it will be conducting here. Similarly, you can see that T3 will be conducting for the period here as well as here. So, this is the case will be continue and that matrix will be actually featured in, and accordingly it will get a voltage. So, this will be the pattern. So, T1 will be conducting for this period as shown here and we can apply a delay to it, and output voltage, since we can change the delay. So, output voltage can be changed depending on the profile, and assuming that load current is almost constant. So, this will be the actually the input current and this will be the fundamental. Same way, if you have actually this waveform where have a large delay angle. So, then what will happen? So, you can see that this will be the pattern. First it will trigger with the T5, thereafter T3, T1, thereafter T3, thereafter T5, and but what will happen? Then you can find that actually lower half will continue as per the sequence. So, for this reason this leads to the actually a discontinuous voltage. We had talked about discontinuous current. So, we will have a discontinuous voltage. When actually it will be discontinuous if the triggering angle will be more than 90 degree in case of the half control converter, 3 phase half control converter, and this will be the this kind of waveform full control. This will be the continuous waveform. So, pattern of the waveform will change till alpha equal to 0 to 30 degree and thereafter alpha more than 90 degree. We shall continue to our discussions with the 3 phase half control waveform with its mathematical analysis in our next class. Thank you.